This is the beginner stage. Um, I am really happy to be presenting what's coming next, and it's particularly interesting after having just gone through sort of like the basics of building a substrate blockchain. Using Frame. What is Frame, right? So hopefully we're more and more getting familiar with these concepts. Um, Today, I have the pleasure to present to you Emre Surmeli, who is a technical educator at Web3, also a colleague of mine. We've worked together on a couple things. We've done a workshop together. So really stoked to have you here, Emre, today. And you're going to be talking about storage on a Substrate chain. Now, I hope that those of you who have been, there were some questions in the previous talk about what does storage look like on a chain? Is it all key value data? Is it all a key value database? Does it happen on the WASM side of things, or is it all on chain? And hopefully, Emery, you're going to be answering these questions today. And I encourage you to keep asking questions, guys. I'm here. I'm moderating. I'm checking what's going on in the chat. So don't be shy. And yeah, let's kick things off. Take it away.
Thank you, Sasha. And thanks to Radha for that cool presentation on Frame. Welcome, future, current runtime developers. My name is Emre. I will be talking to you about storage on Substrate. Yeah, so as we all know, blockchains, the way I like to think about blockchains is that it's just another type of database, but it's different from the types of databases that we're used to with the Web2 applications that we use. It's decentralized, it's public, it uses cryptography, and it has consensus mechanisms that allows the participants on the network to come to agreement on things. And because of these different properties of the blockchain, it forces us to think about storage differently than traditional databases. And so it requires us mostly to think lightweight. And Substrate solves these in its own way. So this presentation is kind of about that. We're going to talk about the different types of technologies we use in Substrate to do storage, such as hashes, maps, and tree structures. So in this talk, we're going to uncover, first of all, the layers that make up storage on Substrate. And the layers are going to be abstracted away into explainable, digestible bits. And then, as we are uncovering these layers, we're going to take a look at what they are under the hood. As a technology, and I tried my best to keep them as simple as possible as I explained them to you. And then after that, we're going to explore some on-chain storage considerations. As I mentioned before, blockchains require us to do our different type of thinking when it comes to storage that tends to be lightweight. So as a developer, as a runtime developer, what are some considerations when it comes to storing values on the blockchain? And we're also going to explore some current best practices. As a developer or prospect developer, we should know that best practices change all the time. But since we've been developing Substrate for a while now, there has been already established approaches to storage that seems to be working well. So what are these abstraction layers? What we're going to do is we're going to explore each layer, and each layer actually interacts with the one below it. And so the first layer are the APIs. These are the available tools that Substrate gives us as a developer to be able to interface with the underlying storage structures. And then under the APIs lives the overlay chain set. This is something like a caching layer. Obviously, we want to reduce the amounts of reads and writes to the database as much as possible. This layer is going to kind of handle that. And then under that layer, the overlay chain set interfaces with the Merkle structures that we have. And these are really cool data structures that allows us to optimize the way that we interface with things in storage. If you already know Generation 1 and Generation 2 blockchains like Bitcoin and Ethereum, you might already be familiar with the Merkle data structure. And then at the very root, at the very bottom, we have the actual database. It's a key value database, and we're gonna peel the, I guess, layers, take a look under the hood as to what that actual database is in Substrate. So let's get right into it. What do these layers look like under the hood? So first, we're going to start with APIs. As I mentioned before, these are the available interfaces that Substrate exposes to the developers. These are the things that the developers are going to be using. So let's start with the simplest. If we're going to be storing simple items on the store, on the blockchain, we're going to be using a storage value. And in a Frame version 2 implementation, this is what it looks like. So here we're setting a storage value item, and we're setting up a optional getter that takes an argument for a function name. And the reason why this is optional is because if you don't set a getter, there's still ways to get values from storage, but without a getter method. So in the very beginning, you see the pub declaration, which means this is a public value. One thing to always consider when you're storing values on a blockchain is that it's a public open database. Here we are setting a storage item called some primitive value, which is a storage value of integer, U32 integer data type. And we're also passing in an argument called value query, which sets abilities for the function to return default values if there is nothing in storage. The storage value is going to be utilized for simple integers or strings and things like that. And then if we want to store more complex items, we can use similar data structures to hash maps. We call these storage maps. And what maps are, if we haven't heard those terms before, it's a key value data store where we can declare the type of hashing algorithm that is used to set the key. And the value can be declared at the definition time of the storage map. So here, once again, we're setting a storage map item. And I did forget to mention in the storage value item, we're using macros. So the pallet storage macros being declared, and then a pallet getter macro is being set with an argument to define the getter function name being passed in there. Once again, this is a public value that will be that we will be setting, and we're using the Blake 2 128 concat as a declaration of the hashing algorithm that we would be using for how we set the keys. One of the cool things about Substrate is that it allows you to choose the type of hashing algorithm that you use for your keys. And here, obviously, we're using Blake 2 128. And then we can start setting hash maps where we have items that might be, keys that might be pointing to the same value, where we have 2 keys for a single value. This is called a double map. And the declaration of that would look like this. And we, similar to the storage map, will be defining the hashing algorithms that we'll be using for the keys. and the type of value, the data type of the value that we will be setting. And then to get even more complex, we can actually create storage nmap items which have an n number of keys. So this could be quadruple, triple keys for a single value. Once again, storage items allow us to define the type of hashing algorithm that we can choose for these. And we can start setting the data types as well for those hashing keys. So these are the different types of APIs, interfaces that Substrate allows the developers to define their storage items. So that's the first layer. The first layer is obviously the one that the developers are going to be typing, defining themselves. And then we're going to start getting a little bit deeper now with the overlay chain set. As I mentioned, this is sort of the caching layer of the storage. So this is the layer that allows us to stage changes. So when you're staging changes, you can think of it kind of like how Git stages and commits changes to remote servers. So it acts as a layer that the data first passes through. This is going to handle any changes that will be made to the key value database at the very base layer. And it optimizes the amounts of reads and writes that goes to that bottom layer. Any changes that need to be made to the DB are committed only once per block. And the types of changes that are handled, and these are the reads and writes to the DB. Those are the types of changes that happen to the DB, are either prospective changes, things that might happen, and committed changes, so things that will happen. So the overlay chain set is going to make sure that it optimizes the amount of interaction that our code, our runtime code, is going to be making with the lower level database structures. So that's pretty much it for the overlay chain set. It's pretty simple. And then we have our Merkle structures. So Merkles are super cool data structures that allows us to, first of all, create light clients. We saw this with the implementation of Bitcoin. So Bitcoin used Merkle data structure to store the transactions hashes. And then the way that it would optimize transaction lookup is by putting it into a structure that we're going to look at. So at Substrate, we use a base 16 modified Patricia Merkle tree. It's a little bit more useful to us for the types of applications that we're building, since we've kind of developed generations of blockchains since Bitcoin, but at the root, it's very similar. So we can visualize a Merkle tree structure like this, where at the leaves, we hold the hashes of the data. And then we hash the pairs together and keep hashing pairs until we get the root hash. And the root hash allows us to interact with a function called the Merkle proof. And the Merkle proof algorithm allows us to verify if a piece of information exists in the blockchain without having to look at the traverse the full data structure, the full tree. So again, in generation 1 blockchain like Bitcoin, this was used to create light clients, where light clients didn't need to hold all the transaction data. They could actually just hold the transaction, the Merkle root of the transactions in each block. And this allowed an easy, verifiable lookup of data in the blockchain. So this is one part of the base 16 modified Patricia Merkle tree. The second part is going to be the Patricia tree. And the Patricia tree is a way to store for example, for us, hashes that have similar prefixes. So in a simplified visualization of this, we have 7 words that's stored in a Patricia tree. And the Patricia tree allows us to put shared prefixes on the edges of the nodes. And this allows for quick lookup of values, keys for us. And the way that we can utilize these structures together is by combining them. We're allowing the Patricia to provide the path of the key that we're going to use to look up values in the database. And the Merkle provides the recursive data structure to hash underlying data into a single root hash. So together they're working to optimize and reduce the amount of data stored, allowing us to store state in a way that keeps blockchains performant. And we'll talk about the performance of these data structures because they're technically not as performant as a traditional centralized database might be, but we're making some trade-offs there that we're comfortable with to be able to make things essentially lighter, which is one of the most important things when it comes to storage on the blockchain. So the data structure of the Patricia Merkle tree, also known as a HashDB, is a data structure that lives on the actual key value database. And this data structure is what the overlay chain set is interfacing with. So why does it do that? Well, it allows us to create unique fingerprints for all the data that lives in a block. And it allows us to create proofs of existence of data. And that enables quick verification, and allows for recursive hashing of data with the Merkle structure. So the implementation of this is a tree developed by Parity, and you can go to github.com/paritytech/try to see the actual implementation. And that implementation allows us to set arbitrary key value lengths to be stored on the actual key value database. And so the reason why we want to do such things is we want to be able to build blockchains that are light. Light clients mainly rely on these data structures to make sure that they can look up hashes of accounts or account IDs, which are hashes, transaction IDs, which are hashes, and then we can store the values in bytes on these hash maps, which are the underlying structure. And these trees are going to give us an easy way to look that up, an easy way to modify the values that live in it. Now, as I mentioned, the reads and writes to these structures are not necessarily optimal compared to traditional databases. And we'll kind of talk about that as we look at the actual key value database structure, which is what we're going to talk about next. So the key value database, or short for KVDB, is going to be a few things. So firstly, the implementation of it is it's a fast embeddable persistent key value storage. This is the actual underlying structure. We implement this in 2 different implementations. We have RocksDB and an experimental ParityDB library maintained by Parity Technologies. It's our own implementation of a key value database. And it's a hash table where we have key values, and the keys are by default Blake 256 hashes. And these are modifiable because Substrate allows us to choose different types of hashes for setting the keys. And as a runtime developer, that's actually a decision that we leave up to you. You can choose hashes that might be quicker, but not as secure. You might, for certain optimizations of certain storage items. And then we also have keys that are arbitrary value lengths, keys that are hashes and values that are arbitrary value lengths. And at the lowest layer, this is where actual data lives. So every single layer that we talked about before this, we have the Merkle structures, we have the overlay change set, and then we have the APIs. All of these sit on top of the actual, where the actual data lives. The abstraction layers built on top of this are optimized optimizations to this layer. And a better way to interface with the data that lives on-chain. So what are some on-chain storage considerations? Now that we understand what these layers are and the reason for them, we can think about how to utilize them as a runtime developer. So we want to make sure that only runtime critical items live on-chain. You might have certain applications that have necessarily things that they might want to store that is not runtime critical, and there are ways to handle that. But one important way thing to think about at first is the chain weight. On this, every kilobyte counts. We want to keep blockchains as light as possible. So data stored on data stored on the blockchain is going to live on each node that runs that chain. So this is why we want to make sure that our storage is kept to the minimum. We have transaction fees. We want to make sure that the amount of data processed doesn't cost more than the computation that is required for it. Most often we pay a base price for the transaction itself, but we also have other considerations, and the read and write time. The read and write time to tree structures is O log n, meaning that n being the number of nodes in a tree structure compared to O of 1 in traditional databases. This means we're trading off lightness for speed, which makes sense for blockchains. And we also have some best practices. So to keep in mind while developing a Substrate blockchain, we want to make sure that we're using hashing to its full capabilities, which allows us to control storage costs by bounding the size of items that are stored. For example, on Polkadot or Kusama, our democracy enactments are a hash of the proposal and not the whole function itself. Runtimes are was and blobs, which are hashed, and the hash is what's being voted on, not the whole runtime itself. So Substrate lets us choose which hashing algorithm we want to use, again, in storage. And then we have some off-chain considerations. We're able to, Substrate gives us some off-chain features, such as off-chain workers. If we want to start storing items that might not make sense to store on-chain, we can take weight off the chain by putting storage items on nodes that might not want to share it with the whole network. And off-chain workers can interact with that. So what those things are what we call off-chain storage, local node-specific storage items. Again, these are things that we might not want to share with every single node on the network. And then we also have off-chain indexing, which allows for actual runtime logic to query off-chain storage. So making sure that we understand that we have these tools to our uses allows us to keep our storage to a minimum. And the way we structure our code is really important. We want to make sure we want to optimize code blocks by verifying operations before emitting them to the chain. So do not use storage for any transient or ephemeral pieces of variables because post-extrinsic dispatch caching happens. So this allows us to utilize checks before we actually execute the extrinsic, before it's essentially written to the DB. So that's it from me. Here's some resources to actually dig deeper into this stuff. I implore you guys to look into the tree structure that we've developed. And yeah, I'll take any questions.
Emre, thanks so much. That was super interesting, and especially that like, storage is like so fundamental in any substrate chain, right? So I think you gave a really great overview. We don't have that much time for questions. I've been looking in the question bank, and there's some interesting ones in here. And I'm kind of just gonna try to coalesce the questions together and add my question too, which is when we're building substrate blockchains, what is it about storage that we should bear in mind? And what is there any tools available, like benchmarking or like ways that can kind of inform better design decisions?
Yeah, what's cool about Substrate is it allows the runtime developer to set the what we call weights, essentially things that impact the transaction fees. And the way we set those weights is by using benchmarking. So as a runtime developer, we want to make sure that when we're developing our runtime code for application-specific chains, we want to make sure that we're only storing the amount of data that's needed. So if you're running a piece of computation, this means that not storing, ephemeral variables that is a part of that computation, but only maybe the outcome of the computation. And yeah, so what's cool about Substrate is it gives you that power as a runtime developer. Yeah.
Yeah, for sure. Yeah, I think that's very well said, very well answered. Well, Emery, that's all the time that we have. Thank you so much for taking the time. This is a really interesting topic, and for those of you watching right now, like all of this stuff exists in very different areas of our docs. If you go to docs.substrate.io and type in storage, you'll find some of these reference material from Emre's presentation.